Okay, into the second subtopic of motion and relativity, and that is force and momentum. And in part A of this video, we're going to look at a bit of an introduction to force and momentum, and in particular, we're going to look at momentum in terms of Newton's second law. So that relationship between Newton's second law, which is the force equals mass times acceleration, or that the acceleration of an object is proportional to the force and inversely proportional to the mass, which leads to that formula, force equals mass times acceleration, and how that relates to momentum. Let's get into it. Okay, so by way of introduction or recap, momentum is given the symbol P, and we put the little arrow above because it's a vector quantity. Direction is important. And if you haven't heard this before, a good way to think of momentum is it's a measure of how hard it is to stop an object. So if you want a picture in your mind of what momentum is, think about a measure of how hard it is to stop an object. And basically that means the faster it moves, the harder it is to stop. That sort of makes sense. And the heavier it is, the harder it is to stop. So if we think about that mathematically, momentum is the product of the mass and the velocity. So momentum equals mass times by velocity. The units for momentum are either kilograms meters per second, kilograms for mass, meters per second for velocity, or we can also use something called newtons, seconds, newtons. Later on when we derive another formula, you probably will be able to see where that comes from. So either of those units is acceptable for use for momentum. Kinetic energy. Hopefully this isn't an introduction to kinetic energy. Hopefully you've heard about kinetic energy before you get to year 12 physics. We use the symbol EK this year for kinetic energy, which is probably in line with what you've done before. And think kinetic is due to motion. So whenever we're dealing with the energy an object has due to its motion, we're talking about kinetic energy as opposed to potential energy. And energy is the capacity to do work. And if you remember back to your early years, work is force times distance. So it's the ability to apply a force and cause an object to move a distance is what energy is. But all we really need to know at this point, kinetic energy formula equals a half mv squared. And I'm hoping most people already know and remember that by now. So the next thing that we need to do is basically derive this formula here using Newton's second law, which is this formula here, and the formula for momentum, and also the formula for acceleration, which I've got here. So we call this formula here that I'm about to derive Newton's second law in terms of momentum, whereas this is just Newton's second law in terms of acceleration, or mass and acceleration. So, how do we derive this formula as it says here? So we know that force is equal to mass times acceleration. We know acceleration is equal to the change in velocity over the change in time. So how fast the velocity is changing. And we can think of change in velocity as Vf minus Vi. So if we substitute, basically initially this equation, I might use a different colour for that, Mark. If we substitute this equation into here for A, and we substitute that formula there for delta V, but I'll do that probably in 2 steps, we get something that looks like this. Force equals mass times delta V over delta T. Then substituting further, we get equals mass times Vf minus Vi. So that's the final velocity minus the initial velocity divided by delta T. And then if we expand that out, we get mvf minus mvi. So force equals mvf minus mvi divided by delta t. But we know, let's use the yellow again, that P is equal to mv. So just let me continue on up here. We know that, therefore, F is equal to PF minus PI over delta T. Therefore, force is equal to the change in momentum, PF minus PI, divided by delta T. And probably for completion, I should say here, I'm just running out of a bit of space, that what we're doing there is saying that basically delta P is equal to PF minus PI. And then we're putting that back into this formula here. So that is the process we use to derive this formula here, which I would refer to as, let's use another colour, Newton's second law in terms of momentum, as opposed to the one in terms of acceleration, which is force equals mass times acceleration. So I think the easiest way to look at the next two criteria here is doing basically an example problem. So draw vector diagrams in which the initial momentum is subtracted from the final momentum, giving the change in momentum, and solve problems in both 1 or 2 dimensions using these formula. So let's have a look at and see what that looks like in a problem, because I think that's the best context to look at. So calculate the magnitude of the initial momentum, calculate the magnitude, just the size, so we don't need to worry about direction because it says magnitude. So yeah, always good word to underline. We just need to worry about the size, not the direction, of the initial momentum of the helium atom. So the formula for momentum is P equals m times v. That is on your formula sheet, but you'll probably remember it without needing to check your formula sheet if you've done enough work this year. And then we substitute in. So always show that substitution step. That's the best way to make sure you get maximum marks in the exam. So that's equal to 6.65 times 10 to the minus 27 multiplied by 1.35 times 10 to the 3 meters per second. And that overall is equal to 8.9. How many significant figures have we got here? 3 significant figures. So we want 8 point, just checking my calculator here, 8.98 times 10 to the minus 24 kilograms meters per second. Just in case there's unit marks for that question, let's be safe and put them in. So hopefully that's pretty straightforward. Part B. On the grid above, draw and label a vector diagram to show the change in momentum, delta P, of the helium atom as a result of the collision. So the speed doesn't change, so the length of the momentum vector before and after will be the same. So if we draw in, let's do different colour there, let's do green for initial. We draw in the initial momentum there, then we draw in the final momentum as it comes off the wall. And so those two things will be the same length. Now we need to calculate the change in momentum. So we need to basically do delta P, which is equal to, remind ourselves these are vectors, PF minus PI. When we subtract a vector, we add the negative, so PF plus minus PI. So minus PI will be, and we use the tip to tail rule. We're going to come back to 2 down. So minus PI is going to be that vector there. So it is equal in length and in opposite direction to PI, minus PI. And that leaves us with the change in momentum vector being this vector here. That is our change in momentum. Now, if we look here, if we put that line there, that angle there is 30, that angle there is 30 degrees. From the diagram, the angle's given. So we have an equilateral triangle. So, we can show that by maybe going dung, 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 all three sides are the same length. Just we realise that's an equilateral triangle. Sorry, we've already drawn that vector for part B. So I'm really moving on to part C, calculate the magnitude of the average force applied to the ball. So the change in momentum, and again, it's the magnitude. We're not worried about the direction because it's just the magnitude, will be equal to, in magnitude, the same as the initial momentum, which is 8.98 times 10 to the minus 24 kilograms meters per second. Because, if you want to, doing it real shorthand there, that's because we've recognised we've got an equilateral triangle. So, to work out the force equals delta P over delta T, and that's on your formula sheet. So then we substitute those values in. Force is equal to 8.98 times 10 to the 24 divided by 2.14 times 10 to the minus 4. That's given to us in the question. And we get left with a force equal to that should be a minus there. I had to pause there and I had to check my calculator. And we get 4.20, three significant figures, times 10 to the 20, and our unit for force is, I think that's minus 20, sorry. Not doing well with my pluses and minuses today. Force equals 4.20 times 10 to the minus 20 newtons. So, hopefully we have displayed everything we have been asked to display just there.